Shall we start?
Thanks everyone for coming. Today we start with David. Good morning.
Thank you, Reed, for the introduction. Yesterday we saw that we saw a very simple idea of trying to certify that a function is non-negative by decomposing it as a sum of squares of other functions. And so one theorem that I want to stress here is mentioned it briefly at the end last time. So if you have a function that has sorry, let me write it differently. So I want to say that there exists an algorithm that can find these decompositions if they exist. There exists an algorithm that given a function f, and here it's important to specify how it's represented. So represented as a multilinear polynomial. And such that this function has a good certificate. Then this algorithm can find a good certificate for a slightly different function. So it's, but it's just the original function shifted by some tiny amount. And this kind of slack will be immaterial for our purposes. It's really very small. And the running time is n to the order d. And this algorithm is it has a sort of long history. So in a certain sense, it started with some work by Shor. Then in a sort of slightly more a comprehensive way, it was explained by Parillo and Lasserre.
That's the Russian show.
Yes, the Russian show. Yes. And but in some sense, so they not Peter Shor. Right? There's, I think Shor also has something to do with the ellipsoid method.
Yeah.
Yes.
This Russian school of optimization.
Yes, exactly. And yeah, and so they related this in some sense related this question to convex optimization questions, and to solve this convex optimization question efficiently, you sort of need some machinery. And I think the paper that people usually cite is this a paper by Krötschel, Lovas, and Schreiber. So those are sort of the references for this kind of algorithm. And then we saw that, so this means that if sort of the degree of the certificates is small, that are involved in the certificates are small, then things are efficient. And when we saw some non-trivial situations where these low-degree certificates exist, like for edge connectivity and for maximum cut and for univariate polynomials. And so this means that there's sort of some looks like there's sort of some algorithmic content in these sum of square certificate. And but so if I say sort of some algorithmic content in these certificates, it's a vast understatement. To a certain extent, this is not just any algorithm, but it's sort of the last algorithm you ever have to know, at least in terms of combinatorial optimization. And so which means that what I mean by that, it's you know, all the algorithms that we know for combinatorial optimizations, they are captured by these low-degree sum of square certificates. Okay. And that means that there are certain that means that these kind of certificates, they will have interesting, they're interesting from a computational complexity point of view. Okay, so let's sort of discuss a little bit about the consequences for computational complexity. Yes? Yes. But so the Gaussian elimination is, so as I said, for optimization problems. And it's not clear to what extent Gaussian elimination is useful for, we don't know of any way of how to use Gaussian elimination for optimization. Actually, I didn't, not sure who asked the question. So you asked the question. Yes. So yeah, yes? Yes. Mm-hmm.
I mean, in the case when D is a constant,
Mm-hmm.
like, can you not reconstruct S from the evaluation? Or not sufficiently very important. So loading equals the number of partially is anyway.
From a sufficient number of points? Yes. I presume, yeah, if you have a carefully chosen set of points, then you could or reconstruct it from other ways. Yeah, I mean, I'm just in general, if I mean, not I think you just have to be careful about how to represent this. You don't like, this is not the only way how to represent these guys. But it's just you need a appropriate representation for these functions. Otherwise, it's sort of not clear what you mean by. So the computational problem is unclear, right? Because if I give you the function as a truth table, as a 2 to the n size truth table, then somehow everything is efficient in the size of the input.
Yeah, but the black box was nice because you can recover from the black box.
Sure, yes, that's right. Okay, so let's talk a little bit about computational complexity. And so the general picture I want to draw first is, so if you look at the kind of landscape of combinatorial optimization problems, so these are all combinatorial. Some problems that are intractable, and so suppose this here separates the tractable problems from the intractable problems, and we really don't have any idea how this curve looks like. What's sort of the difference between tractable problems and intractable problems. And what we know is sort of we have some bunch of examples, some algorithms that show that these problems are tractable. For example, here 0.878 approximation for max cut. That's an example of a problem that we know to be tractable, or min cut is another example of a problem that we know to be tractable. And then we have some problems that we know to be intractable, like sort of any version of clique, or say a 0.99 approximation for max cut. Okay, but we would, it would be really nice if you could somehow get a better understanding of this bigger picture. So what's really the difference between tractable problems and intractable problems? And now one thing that this very general algorithm allows you to do is it gives rise to different, because these kind of certificates, they apply to all of these algorithms. So now you can ask, okay, so let me draw not the true tractability barrier, but somehow the barrier that that corresponds to a low degree sum of square certificates. Okay, so these are problems that have low degree sum of square certificates. These are problems, and everything beyond here doesn't have low degree sum of square certificates. So then, as I said, so all the problems that we know to be tractable, they have these low degree sum of square certificates, and clearly, the problems that are intractable, they shouldn't, they don't have these low degree certificates. Yes.
So this statement you're saying because you went problem by problem.
Yes. That's right. So you have to trust me, and I mean,
There's no generic way to see this. You need to kind of go through.
Yeah, that's. I mean, no, but it's sort of. I mean, there can't be a generic way, right? Because there's no generic way to. I mean, like, so these algorithms, I mean, many of them are sort of ad hoc, or
Right,
they look ad hoc, so you have to check by hand. And yeah, so this barrier, this for the existence of sum of square certificates, this is something that we can hope to understand. And it should be very much easier to understand than this true tractability barrier that we have, in some sense, no idea how to understand at this point. And a nice thing about this is that, once we have an understanding of how this sum of squares barrier looks like, then we can ask, what kind of problems, could be here in this range between, in this kind of range where we currently don't have good examples for. Okay. Or maybe, one could show that this is just empty and there are no problems.
You don't have good examples, or you have no examples?
So yes, so one, so maybe at full disclosure. So I think one problem where things are a bit unclear is maximum matching. Okay, so this is a problem that you can solve exactly in polynomial time. But it turns out that sort of sum of square certificates, they only can solve it approximately with a sort of arbitrary good approximation, but they can't solve it exactly. So that's sort of some difference. But sort of once you allow these certificates a little bit of slack, then we don't have, I don't know of examples where we have an algorithm but we don't have sum of square certificates.
Things from the forbidden minor theory that they also fall under this. The efficient algorithm for deciding whether a graph is perfect.
Okay, yes, so this is a good question. So I mean, this picture is more meant for worst case problems, which of course, like, there's no formal definition of what's the worst case problem, but there's a sense in which, so once you give too much structure to the problem, then then these very general, sum of square certificates, they might not give you the kind of thing. So for example, you could probably come up with some some combinatorial problem, and you consider a special case such that solving the combinatorial problem is equivalent to factoring or something like that. And then like sort of once you can embed sort of some kind of algebraic problems in your combinatorial problem by specializing it, then it's plausible that the sum of square certificates don't work. Yeah, I mean, we're far from understanding all of these issues. One class of problems where it's very clear cut that these sum of square certificates capture the best known things are constraint satisfaction problems, the problems that Eric talked about. But it's not. But sort of just constraint satisfaction problem would also not be an accurate description. Okay, and now so this is the very general picture. Now more concrete questions. So so there's Feige's hypothesis about random 3-set. And what it says is that the hypothesis says that given a random 3-set formula, with n variables and let's say 100 times n clauses, random clauses. That's what I mean by random 3-set formula. It's intractable to certify that the formula is unsatisfiable. So if you pick a random 3-set formula with significantly more clauses than variables, then with very high probability it will be unsatisfiable. It will be far from unsatisfiable even. And what Feige's hypothesis says is that it's intractable to certify the unsatisfiability in this situation. And so just so this is a very concrete question about complexity. But it's also clear that in some of the tools that we usually use to reason about computational complexity, they will fail terribly here, because usually we reason about computational complexity in terms of reductions, and once you have this very specific distribution of instances, just random three-set formulas, then reductions become really problematic, because whenever you apply a reduction, if it's a non-trivial reduction, it will increase the size of the instance a little bit, and then you somehow you introduce some structure to the instances, and they will not you will change the distribution in a significant way. And so it means that this seems very difficult to reason about in terms of the usual computational complexity tools. But now but on the other hand, in terms of sum of square certificates, there's it becomes a very clear question. So then we can look at the function that corresponds to let's say the for a given three-set instance, we can look at the function that counts the number of satisfied clauses. By the assignment x. Now we can ask, is there a sum of square certificate that this, that this function is always smaller than the number of clauses, right? If this, let's say, the function is smaller than the number of clauses minus 1, and this is equivalent to saying that this unsatisfiable. And now you can ask, do there exist sum of square certificates for these kind of statements? And in some sense, if you want to support Feige's conjecture, what you would try to prove is there don't exist these kind of certificates, and that's indeed and people managed to achieve this. So this result by Grigoriev, and then it was maybe I think it was around 99. It was forgotten for some time, and rediscovered by Schönebeck. Not sure if I'm writing this correctly. And so what they say is that with high probability, the sum of squares degree of this function is almost as large as it can be. So we saw that if you have n variables, then the sum of squares degree of a non-negative function can never be larger than 2 times n. And in this case, if you generate these clauses like this, then the sum of squares degree is some constant times n. So in this sense, so one way to interpret this is that so what this shows is that this problem of random three-set is beyond this sum of squares barrier. Okay. And then it's I mean, what we don't know is that it could be here or here, truly intractable, or somehow in this funny range, but that's a different question. Yeah,
Did anyone look into more subtle things? So, for example, presumably, or if you ask the physicists, of course, 4.2, perhaps there is now even I'm sure this will now actually become settled, but the threshold for probability for the Wilsonian lines somewhere around
Mhm.
4.2
Mhm.
times it. So it makes sense to ask various variations about this. So this requires maybe 100. So what I'm saying, the constants now may start to become interesting.
Yes, yes. So that's a good.
But even at 100, you don't know it yet.
No, no.
Put it in your place.
At 100, it's almost surely not satisfiable, but whose conjecture is that it's hard to certify?
No, no, I'm talking about this. This gives you a new way to
Yes, yes.
to state it.
Yes, yes, exactly. So that's
I mean, concretely, is the statement downstairs also true if I replace 100 by 10?
yes. I mean, yeah, you could.
4.3.
Yeah, I think what you're suggesting is, I mean, you could sometimes look at the phase transition for this question, right? You look at the sum of squares degree of this function, and you ask, does it jump? And yes. Yeah, that's a very good question.
It's conceivable that it happens later than started. That would be very interesting to understand.
Yes, yes, exactly. And these kind of questions, right? I mean, here, like this complexity question becomes very unclear how to answer if you play with the constants. But somehow the question about certificates becomes very becomes a well posed question, or you can attack it. Another important situation where sum of squares plays a role is the unigames conjecture. That's a conjecture by Subhash Kode. And so I don't want to define it at this point. I just want to give you the things that you need to know at this point. So it's an assumption about, or an assertion about hardness of some hardness of approximation for some CSP. And at this point, then the CSP is called unigames, but that doesn't matter so much at this point. One important thing is that it's qualitative, in the sense, I'm not sure if there's supposed to be an E at this point here. E.
In German, no?
Yeah, yeah.
Yes.
Yes. So what do I mean by qualitative here is that there are no constants specified. In the assertion, so it's like some epsilon delta kind of statement, and the surprising thing is that if this assertion is true, it implies that this 0.878 approximation for max cut is NP hard to beat. In the sense that getting a strictly better approximation than the approximation that you get from degree 2 sum of squares is NP hard to achieve. And these are results by, let me just list the names, several papers, Coach, Kinder, Mossel, O'Donnell, and okay, now I will butcher his name, Oleskevich. Something along those lines.
Very brave of you.
Yes.
I have a vague memory that there is ESZ. Yeah.
easy angle.
You know, it's that's how you
Yeah, it's okay. It's Z. Okay, now I. Yeah. And ZZ or ZZ? ZZ. Yeah, okay. Okay. Okay, and this is not just true for MaxCut.
What's his first name? Can you remind me?
Yes. And yeah, so this is not just true for MaxCut, but it turns out, for a large class of problems, really a wide range of problems. And this, in particular, was proof. This follows from some work of Raghavendra. So those are some of the people involved, but there are many more people that contributed to this. Very exciting kind of story. And now, what does so what is the perspective on this that you could get from sum of squares? So this in particular implies that if you look at this function that we looked at before, that counts the number of edges that are cut by a partition, then right, if this is NPR to beat this approximation, it means that the corresponding certification question should not have low degree sum of square certificates. Okay? And so it means that if I look at function if you look at this kind of function, and we get a MaxCut value of a graph minus a little bit more than this constant that you get from degree 2 sum of squares. So this here, if you look at this function, there should exist graphs. So if the James conjecture is true, then there exist graphs G such that this function here has sum of squares degree at least n to the order 1. Okay, so this is under some conjectures like that, similar to P not equal to NP. Okay, you should have, if the James conjecture is true, then there should exist graphs such that this non-negative function on the hypercube has very large sum of squares degree. And so this is something that we could try to understand, but this is something that unlike this question is we don't understand it. And actually there are some sense which I will talk about today that there's some evidence that going from degree 2, which is really the constant that you have here, to a degree to some larger degree 4 or some larger constant, it really makes a qualitative difference in what sum of square certificates can achieve for these kind of functions. Okay, and that sort of I think it's a very outstanding question to try to understand whether there are graphs like that.
What are candidate graphs?
Yes, so that's exactly the problem. So we don't have candidate graphs, and actually all graphs that we that it could, that were candidates at some point, we could verify that degree 4 or degree larger gives you better guarantees. For all candidate, where you sort of want sort of some infinite family of graphs, and then you want to analyze the size of the sum of squares certificates for those, basically for all graphs where the degree 2 is tight, for all constructions where we know that degree 2 is tight, actually degree 4 gives you a better bound. So here in these sum of square certificates, your freedom is to you can either allow degree 2 certificates or larger degree certificates. So that somehow determines on some level it corresponds to the running time that you're willing to spend to find the certificates. And the Gomez-Williamson algorithm corresponds to degree 2 sum of square certificates. And if the Huygens conjecture is true, then looking at certificates of larger degree should not give you better guarantees.
So which examples were tried?
So they are related to the noisy hypercube, and I will talk about those. Right. Yes. So there's also a sense in which expanders are not problematic instances here. Expanders actually even degree 2 is better, gives better guarantees for expanders. Okay. So I want to very briefly also talk a little bit about. Okay, in some sense. You can also ask, what does sum of squares tell you about P versus NP? Of course, this is there are some serious restrictions here, but nevertheless, it makes sense to ask. And in particular, so there's some very nice work by Yannakakis from the 80s. And what he does in this work, he formalizes a notion of LP linear programming, and sort of, in some sense, this notion also applies to semi-infinite programming algorithms. So he formalizes a notion of what does it mean to use linear programming or semi-infinite programming to try to solve a combinatorial optimization problem. And this is like a very general class of algorithms. And he asks, can this, can they solve NP-hard, or asks us to prove that they cannot solve. Or the goal is to, or the challenge is to prove that they cannot solve NP-hard problems. And notice that this is not a question about, sort of, is it true or not? Of course, we don't expect these algorithms to be able to solve NP-hard problems, but nevertheless, it's a very interesting challenge to be able to prove that they cannot solve NP-hard problems. And this has been open for a while. So he showed for some further restricted classes of algorithms, indeed they cannot solve NP-hard problems. But some couple of years ago, Fiorini et al. They showed this is they proved this for LP algorithms. They showed that Yannakakis' notion of LP algorithms cannot solve NP-hard problems in polynomial time. And in the lecture on Wednesday, I want to talk about a recent result by Lee, Raghavendra, and myself. Yeah, we showed the same statement for SDP algorithms. And what's the connection to sum of squares here? And let me just say it. The way this proof here works is that we prove that actually general SDP algorithms are, under certain restrictions, no more powerful than low-degree sum of square certificates. Okay. So there's a sense in which the sum of squares, these low-degree sum of square certificates, capture the full power of general SDP algorithms in the sense of Yanakakis. And then this, I just erased this picture, but in some sense, so if you have this picture of these combinatorial optimization problems, and you have this tractability barrier, and then you can draw a sum of squares barrier, and then you could also ask, okay, what's the kind of thing that general SDP algorithms can achieve? And what this work shows is that actually the sum of squares and the SDP barrier, they coincide. So there are no problems in between. Okay.
So they coincide, but or sum of squares are
No. So sum of squares. So they are captured by Yanakakis' model notion of SDP algorithms. So they cannot be better. So, okay. So now we have talked about these low-degree sum of square certificates, and it's the definition is extremely simple. You have a function, and you want to decompose it as a sum of squares of low-degree functions, and but it turns out that it's sort of hard to reason about those certificates directly, and a key ingredient to be able to reason about these certificates in a better way are objects called which we call pseudo-distributions. So these objects they turn out to be exactly the dual objects for dual to sum of square certificates. And they really help you a lot in terms of reasoning about those certificates. But they are, in some sense, they are also interesting in their own right. And so one way to think about them, sort of in their own right, is that they give a notion of probabilistic beliefs under bounds on computational resources. Okay, so if you try to say what are your computational beliefs, but your computational resources, sorry, what are your probabilistic beliefs, but your computational resources are bounded, and in some sense these kind of pseudo-distributions they are one way to formalize this. Another way to think about this is that it's a sort of generalization of probability theory where you allow negative probabilities, but the negative probabilities are so that a computationally bounded agent cannot detect the negative probabilities. So that's on some level the the intuition about those.
Computationally bounded or like space bounded?
No, so yes. So what do you mean by computationally bounded? So in some sense, it's the computation should only use things that have low degree sum of square certificates. So in a sense, it should be bounded in terms of these sum of square certificates. But if that's sort of your model of computation, then in the sum of squares model of computation, the agents are computationally bounded. Okay. And okay, so I think the instead of sort of explaining them in terms of dual objects of sum of square certificates, let me contrast them to regular distributions. Okay, so what's a distribution? A regular probability distribution. And we talked about here about distributions over the hypercube. Okay, I can represent such a distribution as a function on the hypercube that takes real values. And it has two properties. One is that it's always non-negative, and that the sum of the values is 1. Okay, so that's what it means to have a probability distribution over the hypercube. Now, let's sort of look at the more functional characterization of these distributions. So if I have a distribution, I can look at the expectation of a function under this distribution, which is just the. Yeah, I realize that this is what I'm writing is trivial, but it sort of it will help when we go to to see it in comparison to what we do with pseudo-distributions. So this is the notion of expectation under the distribution. And notice that we can characterize these distributions just in terms of this expectation operator, because this condition here is equivalent to saying that the expectation of the constant 1 function is equal to 1. And this condition is equivalent to saying that the expectation of every non-negative function is non-negative. Okay, for every function that is non-negative, I want that its expectation is non-negative. Okay, that's equivalent to this statement under this definition. Okay. Now, what is a degree D pseudo-distribution? So it's also a function on the hypercube. But it will turn out that unlike here, it can have negative values. But in terms of the functional definition, it looks very similar to an actual distribution. So here, we will use as a notation, instead of this E sign, we will use E tilde, just to remind ourselves that this is not an actual distribution, but it's the same definition, just the linear form corresponding to this function, linear function corresponding to this function. And the conditions are, so this here is just a notation. The conditions on what it means to be degree D zero distribution is, at first we want that, okay, so this here we will call the pseudo expectation of F under D. Just a name, a suggestive name. So this should be the pseudo expectation of the constant 1 function should be 1, and for every square, and every square of a function g with a degree at most d over 2. Every such function should have its square should have non-negative pseudo expectation. Okay, so this is a weaker statement than this statement. And so since here this, and you see that if you would choose d to be if you would choose d to be 2 times n, then here we would capture all non-negative functions. Yes, it coincides. Yes, it. Okay. Okay, just one remark. So it's a slightly unfortunate terminology. So degree d pseudo-distributions. So these functions, they don't really have. I mean, they don't necessarily have degree d. So they
Like against degree d.
yeah, they are sort of against degree d. Against degree.
They can have.
Say again?
They can have degree.
Exactly, they can have degree d. That's a good point. So you see that in what sense can they have degree d? So so you see that the conditions that we impose on a pseudo distribution, they only talk about the correlation of capital D with functions of degree at most d, and this means that like these conditions, they really only restrict the degree d part of the function capital D. Okay. So
This follows again by Carter-Dorian, more or less the same argument that you said.
yes, or somehow like the fact that if you look at the inner product of yeah.
P, right? I mean, you have the system. No, the fact that just enough. That it's enough. We may assume that D itself, big D, is itself of the great most D.
Mm-hmm.
If this system is satisfiable, then
Yes, that's right. Yes.
Because all the conditions are on like this. You can write the correct
Yes.
representation of
Yes,
P, and all the conditions are on the
Exactly.
titles of the side.
Exactly. That's right.
everything else is orthogonal.
Yes, exactly. Yes, exactly. And so what's the theorem here? If you have so for every function, for every non-negative function, either its sum of squares degree. So here, what I'm stating is the duality between pseudo-distributions and sum of square certificates. So for every non-negative function, either its sum of squares degree is at most d, so either it has a low degree sum of square certificate, or there exists a degree d pseudo-distribution capital D, such that the expectation, the pseudo expectation of the function under D is negative. Okay, and also like just as a sanity check, suppose I'm looking at D equals to n or 2n. Okay, so then like this statement is just is always true for a non-negative function, and then okay, I guess maybe I don't need this condition here, just to make it a little bit, just to make it a little bit more interesting in the case that D is equal to D is very large. So then somehow, if suppose D is equal to 2n, then if this doesn't hold, it means that the function is actually not non-negative. There's a negative point of the function, but then of course, if the function has a negative point, then there exists a distribution under which f has negative expectation, and the distribution just puts all the mass on the points where the function is negative. Okay, but it's true in general, and the proof is like Ignati would say, it's just linear programming. I think you were about to say
You
it.
said because I was about to say
Yeah.
that's obvious, right? It's not really a theory.
No,
It's
yes,
not
yes, yes.
to explain it, so
Yes,
I-
yes.
I-
Yes. So,
Where is your middle name?
my last thing.
so let's prove that. Yeah. So let's look at the situation. So what does it mean that that f has some squares degree at most d? So that would mean that you look at the at the cone generated by functions by squares of functions with with degree at most d over 2. You look at this cone and you ask, and so the question is, whether f has some squares degree at most d is equivalent to asking whether f is contained in here or f is outside of the cone. Okay, and so either f is contained in here, or if f is outside, then there's a separator that through the origin, a hyperplane that separates f from this cone. And if you look at the normal of this hyperplane, that will be exactly this function capital D. Okay, so this hyperplane, you can describe it as all points D. Sorry, all functions F, all functions H, such that this is 0. So this is the form of the hyperplane, and then here, and all these functions have this linear form is not linear function is non-negative, and but at f it's negative. Say again? So you're saying that I should draw the normal in this direction? Okay. Yes. Yeah. Sign this thing. Okay, but that's the picture. And actually, I think maybe a cute exercise is to verify that this cone is closed. It's not trivial, but it's true. Okay.
So actually, it's still on the board. This is what you said. The dual you see on this board.
Yes.
Second line.
Yes.
This text and this picture say the same thing.
Yes. Exactly. Yes. Okay. So now, is this? Okay, now let's use these pseudo-distributions. Okay, so I was thinking about whether to skip one of the things. Maybe let me just briefly explain this part. So it turns out that you can use these pseudo-distributions also to explain this this algorithm that I stated before without actually proving it. Where I was asserting that you can find these certificates. Okay, and so by the duality thing, it's enough to instead of finding these certificates, it's enough to find the pseudo-distribution. And finding the pseudo-distribution is a little bit simpler to describe. And one way to find these pseudo-distributions is using gradient descent.
Using the algorithm yesterday at the end of the talk?
So I mean, yesterday I didn't really explain the algorithm. I just explained that that it's related to positive semi-infinite matrices. And so, if you're familiar with semi-infinite programming, then that's almost enough to see why the algorithm works. Yeah, so maybe let me just very briefly say like a direct way to see how you can find these pseudo-distributions. And so you can set up a function on these a convex function on the space of these kind of functions. And what this function is trying to do, it measures so you're trying to find a pseudo-distribution where the expectation of f is negative. And so let's look at this kind of function. For all g with degree g.
So then, what is a field?
So I want to explain one way to find these pseudo-distributions efficiently using. So given f, if suppose there's no certificate, and can we find the pseudo-distribution?
So now they say there exists. You're now telling us how to do this in efficient.
Yes, exactly. Yes, and so one way, I mean, in some sense, solving a semi-different program, but it's a simple semi-different program, and it's you can almost you can just see directly how things work. And so if you look at this function, so phi of d, so the claim is that if d here would be a pseudo-distribution that satisfies, if d satisfies these conditions, then phi of d would be negative. Okay, so it would so this here would be negative, and here if d here is if it's an actual pseudo-distribution, for every g this is positive, and so if you want to minimize this, you would choose g to be 0 or so, and then this part would be 0. Okay, so if d is an actual pseudo-distribution, and on the other hand, you can also check that if this function here is if it is negative, then you're sort of close to a pseudo-distribution that satisfies this. Okay, because you're trying to say again? Yeah, exactly. So m is think of it as a very, very large number, so something like n to the 10. Then somehow if this whole thing here is negative, it tells you that this here for every function g, this cannot be this is always at least a minus 1 over m, and on the other hand, this here should also be negative, and so this is indeed enough. So finding a pseudo-distribution is that satisfies these conditions is the same as finding some. The goal is to find d such that this here is negative. You can also check that that this phi here is convex, and so it means that the only thing that you have to do is to minimize this this function phi. You only have to be able to compute the gradient. Okay? So that's the question. So what's the gradient of this function phi? And this is actually the gradient of this function phi is just f minus m times g squared. So sorry, the gradient of phi at some point d. It's just f minus m times g squared, where this g here is the minimizer of this part here for this function capital D. Okay, so it means that in order to compute the gradient of this function phi, you just have to find the function g that minimizes this. And if you look at this, then you see that what we're trying to do here is so what we have here is a quadratic form in G. So we're trying to minimize a quadratic form in G. And this is something that, that you can do using eigenvalues. Okay, so there's sort of, you have here a quadratic form, you compute the, the corresponding matrix of this quadratic form, you compute the eigenvector with the smallest eigenvalue, and that gives you this function G. And then and that means that you can compute the gradient of this function phi, and that means that you can approximately minimize it by just doing gradient descent. If you are at a point D, then you go to a new point D prime by adding a little bit of the gradient. And okay, so I ignored some details, but you can actually make this into a polynomial time algorithm for max cut and things like that. Maybe erase this part.
There's no rounding in this algorithm?
I mean, you're not trying to solve a combinatorial problem.
Just the value.
No, you're trying to find this this pseudo-distribution. So in some sense, like that's the SDP solution. You're trying to find the SDP solution, and for that, it's just you don't have to do the rounding. Yeah.
Okay, so you didn't avoid it, so you just stopped one step before.
Yes. But so that's sort of something I want to talk about next. Yes, how to use these pseudo-distributions. Right, so I introduced these pseudo-distributions with the promise that they allow us to reason about sum of square certificates in a better way. And let's see this for the example of max cut. So let's sort of yes.
So this is computing. You said either there's a certificate of degree equals D,
Yes.
or there's pseudo-distribution. So this algorithm, if there's a pseudo-distribution, it will find
It will find it, yes.
And if there doesn't exist one, it will.
Yes, so that's a good question. So in some sense, it should give you a sum of square certificate on somewhere. I would guess it does, but I don't directly see where what's the direct way to get the sum of square certificate if the algorithm fails. Yes, a very good question. Yes, I was hiding this. Yes, so yes, so your question was, one condition on D was also that the sum of the values is equal to 1, and we hit this under the rug. But what you can do with the gradient descent, you can do gradient descent on this affine subspace of functions where the sum of the values is equal to 1. So you do you sort of try to do you want to do gradient descent on this subspace, and the way you can do this is that the only way you have to modify the algorithm is that after you compute the gradient in the same way, and now instead of just adding the gradient to the function, after adding the gradient to the function, you also project in a Euclidean way down to the subspace again. Okay, you do an orthogonal projection onto the subspace. So you first add the gradient and you project to the subspace again, to the affine subspace. Yes. But yeah, very good point. Okay, so let's look at the Gibbons-Williamson algorithm for max cut. How we can describe it in terms of these pseudo-distributions. Okay, so let's recall. So we have this function that corresponds to max cut. We sum over the edges of the graph and count how many of them are cut. Now we have some let's say some value. Okay, so now we have some value C. Okay, and this is sort of our guess for the value of the maximum cut. And then, you know, by this statement, either there exists, this has a degree 2 sum of square certificate. Either I can certify that for every value C, either I can certify that the value is at most, the max-cal value is at most C. And maybe let me put this, maybe put some epsilon here. Either I can certify this, or I can find or we can find a pseudo-distribution D such that the pseudo-expectation of our function f sub g under this distribution, under D, is at most, is at least C.
And this D has degree.
So here degree 2. A degree 2 pseudo-distribution. Yes. Now the goal is, given this degree 2 pseudo-distribution, the goal is to find a cut for the graph that whose value is roughly equal to C. Okay. So how do we do this? Where is this part? The algorithm works as follows. So the first step is that we sample a Gaussian vector xi in Rn with the property that the expectation of xi is the same as the pseudo expectation under D of x, and the expectation of xi transpose is the same as the pseudo expectation of x transpose. Okay. Say again? X. X is this x. So yeah. So what does this mean here? So I did. So I cheated here a little bit. So how did I cheat here? So before I used this notation just to measure the expectation of a function. Okay. Now here what this here is the way you can think about it. The way you should think about it is this is a matrix valued function on the hypercube. Okay. For every point x of the hypercube, it gives me a matrix XX transpose. And now I can look at the pseudo expectation, right? Okay, first of all, like all the expressions that I'm writing with this tilde up front, you should first try to interpret without the tilde, just to make sense. So then here you would have an expectation of, under some distribution of the matrix XX transpose, and the distribution is over the hypercube. So you sample a point from the hypercube, get a point x, and look at the expectation of the matrix XX transpose. And and if you have the tilde thing, it's the same. You have the same expression. Yeah. And the same here. So here you have you sort of average over matrices. Here you average over vectors. And so what we do here is the goal is to sample a Gaussian vector with whose first moment is the same as the first pseudo moment of x, and whose second moment is equal to the second pseudo moment of the pseudo distribution D. And so let me delay a little bit the discussion how you do this. And the second step is that you output the vector x prime on the hypercube. And you get by choosing x prime, the ith coordinate of xi to be the sign of xi I. Okay, I should say that there are other ways of, this is a sort of an unusual way of describing this algorithm. I mean, describing it mostly because it gives some general perspective on how to use these pseudo-distributions, which will be useful later on. But you see that, I mean, after sort of, okay, so I didn't explain how you can sample such a vector or why such a Gaussian vector even exists. But once, I mean, if you sort of take this as a black box, then it's a very simple algorithm. Yeah, and maybe to explain this a little bit better. So,
Oh, wait, this sampling doesn't even know the graph? X.
say again?
Ah, I see. D depends on the graph.
D depends on, yeah, so we computed D such that it satisfies this condition. Yes. Okay.
It's like matching the first and second mode.
Yes, that's right. So you this Gaussian vector, it matches the first two moments of the pseudo distribution. Yes. So let's start. Let's discuss why this exists. So in general, a Gaussian distribution. So if you ask, I want a Gaussian distribution with this expectation and this covariance, then it exists whenever, as long as the covariance matrix is positive semi-infinite. Okay, so what we have to check for the existence of this Gaussian distribution is whether the covariance matrix, which which would be this matrix, where mu is the mean of this pseudo distribution. We want to check whether this is PSD. This matrix is positive semi-infinite. Okay, and so first let's why is this positive semi-infinite if D would be an actual distribution? So then here this would just average these matrices, and each of these matrices is positive semi-infinite. Okay, so if D would be an actual distribution, it would be, for trivial reasons, this would be positive semi-infinite. So that's good. And now, so why is it positive semi-infinite in our case? So let's just evaluate the quadratic form of this guy. So we are supposed to take some arbitrary vector v and multiply from the left with v transpose and from the right with v. Okay, so we want to understand whether this is non-negative. You want to show that the quadratic form evaluated at any point v is non-negative. And now you see that this here is just it's just linear. Okay, so you can move the v transpose inside, and so far it goes like this. So that means that this is the same as, by linearity, this is the same as moving v inside. And once we move v inside, then it's v transpose times this guy, and this x minus mu transpose times v. So that's just this is just quadratic. Yes. So this linear product of this linear. So this is a linear function in x squared. Okay, so now we have the pseudo expectation of this linear function, of the square of this linear function. Okay, and because we have degree 2 pseudo distribution, it means that for every linear function g, the pseudo expectation of g t squared is non-negative. So, so g would be this function in this case. Okay, so that's indeed non-negative. Okay, so this means that at least the Gaussian distribution exists. And now, so it's a simple fact that if I give you a mean and a covariance matrix and ask you a sample from a Gaussian distribution with that mean and that covariance matrix, that's something that you can do in polynomial time. Okay, so that means that this is actually an algorithm. You can actually run it. Now the question is just what are the guarantees of this algorithm? Sorry, say again? D, yes. So you use it to compute. No, sorry. That's what we discussed before. How to find D using convex optimization. I see. That's 10 more minutes. So what's
The algorithm is find D and then run subroutine on the right.
Yes. And then we saw that you can actually run this these steps in polynomial time. And now that you have to see what are the guarantees. So the claim is that for every I and j, if you look at the expectation of the event that xi is different from xi prime is different from x prime j. So this here is just the event that xi prime is different from x prime j. This probability is at least 0.878 times the corresponding probability in the pseudo-distribution. Okay, so this here is sort of a proxy. You can think of it as the pseudo probability that xi is different from xj, and this relationship tells you that you lose at most a factor of 0.878 by going from x to x prime. Okay, so okay, I think like this is okay. So I think the most important observation about this question is that it's just a question about two variables. Okay, and so it it shouldn't be hard, and actually with a little bit of work, it's actually just a question about one variable. So let me sort of tell you why it's just a question about one variable and draw some picture, and then I think not do the full calculation. So so the first some simplifying step. So we can assume that the expectation of xi and the expectation of xj, and this is equal to 0. Sorry, here I mean the pseudo expectations. So why is that? The reason is that if you have a pseudo distribution D, then let's say D of x, then for max cut, you can also look at sort of D of minus x as a pseudo distribution. Okay, so that's just sort of you reflect the function. And for max cut, if you have if you look at this function at x and minus x, it gives the same value. So it means both of these pseudo-distributions are sort of the same quality. And that means you can average those two guys, and you get a new pseudo-distribution. And after averaging, this guy will certainly satisfy this property, because it, then it's an even function, and so these odd moments will vanish. Okay, so that's good. And so this means that if you look at so the covariance of these two guys, xi, xj, it really looks, it's just, so this determines the distribution, because the mean is 0, and so then this here is the covariance, and this determines, the distribution of xi I and xij. And this guy, so here we know that, so here this would be the expectation of xi squared, but we are over the hypercube, so this is 1. So it means that the only free parameter is the expectation of xij, which I wrote as rho here. Okay. And that means that now what we have is this, we have a Gaussian, we have two Gaussian variables, xi and xj, xi I and xij, and they have this covariance matrix, this covariance, and have mean 0. Yeah, sorry. Yeah, and yeah, but we set things up so that this is the same as the covariance of the Gaussian variables, and this is now an actual distribution. Okay. And so this means that, okay, so now this sort of these kind of standard calculations with Gaussian. So I now I look at I have one Gaussian variable xi I, and now I can express xij as rho times xi I plus something that is orthogonal to xi I, and then the picture is that say again. I guess I don't know what's the usual convention. I guess I meant the part of xij that is orthogonal to xi I. Okay, I'm not sure what's the.
No, they're just saying that the index of j and not I.
Yeah, but that's
Yeah, but it belongs to j, no?
Yeah, but it's orthogonal to xi I.
Yeah, it's 50. Yeah, it's one vertex. Yeah, one vertex against the other. So but let me. So let me write like this. So then, what this achieves is that this guy has also variance 1. Okay. Now the picture is that we have this two-dimensional plane where we sample two independent Gaussians with variance 1. So this is xi I and xij, the orthogonal part of xij. Or xi I. I guess we can. We don't need an index here, right? Okay. Good. And now we. So that's now the experiment. So we sample these independent Gaussian variables, all both with variance 1, and now and then we look at the sign of xi I and the sign of xij. Okay, and the sign of xi I, okay, that corresponds to this line. So xi I is 1 on this part, and xi I is -1 on the other part. And now, okay, now a bit more complicated. Okay, how does the sign of xij look like here? And I think the way you do it is that you you draw this point rho and 1 minus rho squared. Suppose rho is negative, which is sort of the kind of thing that that you would expect in this case, because you try, these guys try to be different from each other. So maybe this point. So this point here is the point with coordinate rho along this coordinate and 1 minus rho squared in this area, this coordinate. I guess it should be. Okay, it should be upstairs again. Yeah. Okay, and then what we do is we sort of draw the normal to this point, and think how does it work? So it should be it will be positive on all these parts. Okay, and now you see that sort of this. Is there color? I think there's color. This here would be the region where both of them are negative. And this here is the region where both of them are positive. And now you can compute the volume of this region, the Gaussian volume of this region, as a function of rho. And that's a simple computation, by rotational invariant, because somehow if you project it on the unit circle, this Gaussian vector that you sample will be uniform over this circle, and so it just depends on the angular. So this is just a function of this angular thing, and then you do some trigonometry, like sine and cosine and all these things. Okay.
Can you summarize? So what did we see? I guess you wanted to show us an alternate way to see the Goldman-Williams algorithm.
Yes. Yeah, okay. Yes. So this is a good question. So in what sense does this give a more general perspective on this algorithm? Yes. So this is, I think, okay, this is a good idea.
I think it's a good point to remind or tell people what this number 0.878 is.
You mean
that would explain, I guess. This is how. So it seems like this calculation eventually is. I mean, it couldn't be anything else. It's the same calculation that.
Yes. No, it's exactly the same calculation. Yeah. No, in some sense, it's also the same algorithm. So let me just try to give a little bit. So what's sort of the general idea behind these algorithms? So one way to think about them is that the pseudo-distribution that you start with, it on some level, what you would really like to do is if this pseudo-distribution would actually be a distribution, you would like to sample from this distribution, okay? Because then if you could really sample from this distribution, then in expectation you really get you would get this value, okay? If D would be an actual distribution and you could sample from D, then in expectation you would just get this value, okay? But the challenge is that, as we said before, in some sense, the conditions that we have, the restrictions that we have on capital D, they only talk about the degree, some low degree part of this function, okay? So it means that like really what we're supposed to do, we're supposed to look at the low degree moments of a distribution and then come up, as a function of these low degree moments, come up with a good solution. And it turns out that if you're just given the low degree moments of a distribution, it's really hard to sample. It's also computationally, in a formal sense, hard to sample. But also it doesn't seem to be the right way to think about the problem. So a different way of thinking about the problem is that you're giving this low degree information about the distribution, and you're trying to combine the points in the underlying distribution to a new solution. Okay, and let me make this maybe a bit formal. So there's an alternative interpretation of this Gaussian vector, which is sort of cute. So just 2 minutes. So suppose that D, yeah, let me erase this part. Suppose D is an actual distribution, and it's uniform over points x1 up to x capital N. And the kind of situation that you should think about is that really that we have an exponential number of these points, okay? And we try to figure out what's, given the low degree moments of this distribution, what, can we extract, from this information a good max cut. And what this and it turns out that you can think of this Gaussian rounding here as combining these guys in the following way. So you sample independent Gaussians, standard Gaussians, G1 up to a G capital N, and you look at the vector xi, which is G1, sort of, G1, Gi, xi. So you sum up the solutions weighted by the Gaussians that you sampled. And if you do this procedure, you will, okay, so I think you have to divide by root n. This procedure will give you exactly this kind of distribution. Okay, and and this kind of distribution is unique. So, so on some level, if you had an actual distribution, this Gaussian rounding, one way to interpret it is that you just take a random linear combination of the support of your distribution. And so the question is, somehow this is, could there be other ways of combining combining these solutions in a way that results into better guarantees, and it just uses low degree moments. Yes, and I think in the next lecture I will talk about how there's a problem called small set expansion, which really seems to be at the heart of the linear games conjecture, and there there's sort of a hard instance called the noisy hypercube, where degree 4 can do better than degree 2, and this is sort of one of the few examples where that happens. Okay, thank you.